Welcome to this explainer. Today, we're diving into what I can only describe as a microscopic, high-stakes molecular heist. And the target? Humanity's absolute deadliest superbugs. You know, for decades, the medical community has been locked in this escalating arms race against antimicrobial resistance. And let's be honest, we've kind of been losing ground. But there's a massive shift happening. Recent breakthroughs from Biosortia represent a fundamental change in how we attack these pathogens. We aren't just hunting for new antibiotics anymore. We're looking at highly sophisticated, engineered mechanisms to literally tear down the walls that protect these superbugs. It's this incredible mashup of biology, genomics, chemistry, and artificial intelligence, and we're going to break the whole thing down right now. Here's our game plan for today. We'll start with the biofilm fortress, then move to unlocking microbial dark matter. Next is the four-pillar solution, followed by dismantling the matrix armor, and we'll wrap up with the future of therapeutics. Okay, let's dive into this. Section 1, the biofilm fortress. So when we picture bacterial infections, we usually just imagine these free-floating individual cells swimming around, right? Well, that's really not how they operate in chronic infections. They form what are called biofilms. Basically, you can think of a biofilm as a heavily guarded fortress. These are highly organized communities of microorganisms that embed themselves inside this thick, physical extracellular matrix. It's literally armor. It shields the bacteria from our immune systems and physically blocks your standard antibiotics from ever getting inside. This fortress is the real driving force behind antimicrobial resistance. It's what turns standard infections, like those on medical implants, catheters, or chronic wounds, into these nearly impossible-to-treat medical crises. And that brings us to a huge, compounding problem known as Eroom's law. Yeah, that's literally Moore's law spelled backward. It perfectly describes this mathematically driven, decades-long decline we're seeing in pharmaceutical R&D productivity. Basically, traditional drug discovery is hitting a massive brick wall. We've exhausted most of the accessible natural compounds we can easily grow in a lab, and clinical trials for new synthetic chemicals just keep failing. Meanwhile, the capitalized development costs have skyrocketed to an estimated $1.4 billion for every approved drug. So, just as these biofilm fortresses are getting tougher and more resistant, our traditional pipeline for building weapons to fight them is totally drying up. Which leads us to Section 2, unlocking microbial dark matter. Now, I want you to really think about this for a second. How exactly do we find the weapons to breach these microscopic fortresses when our traditional methods of discovering drugs are just failing us? I mean, if we can't grow new solutions in a standard petri dish anymore, where on earth do we look? Well, the answer lies in an absolutely astonishing statistic: 90 to 95%. That is the estimated amount of microbiome-derived small molecules that remain completely structurally uncharacterized. Scientists actually call this microbial dark matter. See, in nature, microbes have been waging out-and-out chemical warfare against each other for billions of years. They've been evolving these perfect master key molecules to breach each other's defenses. But because we simply can't cultivate the vast majority of these microbes in a laboratory setting, 90 to 95% of these naturally evolved weapons have remained completely invisible to us, at least until now. Enter Biosortia's industrial-scale microbiome mining, or ISMM for short. Instead of trying to coax a single bacteria to grow in a lab, ISM just harvests intact microbial communities straight from nature. And we're talking on a massive kilogram-to-ton scale. They completely bypass that frustrating laboratory culture bottleneck. But they don't just stop at the harvest. They use proprietary AI to computationally map this chemical dark matter. We're talking advanced in silico discoveries that are deeply rooted in biology, genomics, and chemistry. The AI actually computationally vets these uncharacterized molecules for drug-likeness before a human ever even picks up a test tube. It dramatically accelerates the timeline from raw dark matter to functional therapeutics, a real game changer. All right, moving on to Section 3, the four-pillar solution. Thanks to this advanced in silico discovery, Biosortia has patented a coordinated four-step tactical squad that's specifically designed to completely breach those biofilm fortress walls. We're going to look at patents 19 through 22. Step 1 disrupts the enemy's communications and their membranes. Step 2 degrades the protective protein gates. Step 3 smashes right through the heavy polysaccharide armor. And Step 4 acts like a molecular shredder, cutting the structural DNA scaffolding to just collapse the fortress entirely. Let's see exactly how that works in Section 4, dismantling the matrix armor. Now, what's really interesting about this slide is the opening move for patent 19. highly specialized molecules, specifically amphipathic macrocyclic agents, engage the matrix. What they're doing is called quorum sensing modulation. Essentially, bacteria communicate chemically to coordinate their defenses. Pillar 1 actively jams those communication lines, but at the exact same time, it physically interacts with the bacterial membranes to reduce their adhesion to the surface. So it's basically a targeted blackout of the enemy's command and control. Pretty brilliant, right? Next, the heavy artillery rolls in with patents 20 and 21. For patent 20, we have synthetic protease mimetics. These are engineered to mimic natural enzymes, actively degrading and loosening the protein components of the biofilm matrix. Think of it as melting the fortress gates. Then, patent 21 targets the really tough cross-linked polysaccharide or PNAG strands. It uses a technique called multidentate electrostatic disruption. That's a mouthful, but it simply means these molecules competitively displace the bonds that hold the armor together. They don't just gently push on the walls, they literally cause the structural polymers to swell, loosen, and ultimately shatter, which massively increases the matrix's permeability. But, a fortress still has its internal scaffolding, and that is exactly where patent 22 comes in. Many biofilms use extracellular DNA, or eDNA, as a sort of sticky scaffold to hold the whole shebang together. Patent 22 introduces metallocatalytic macrocycles. You can think of these as structurally constrained molecules designed specifically to trap metal ions, like zinc. By positioning a reactive base right next to that trapped metal, it becomes a literal molecular shredder, actively cleaving the bonds of the eDNA. And once you shred that scaffolding, the entire fortress collapses. It leaves those previously protected superbugs completely exposed to standard antibiotics and, of course, our own human immune system. And that brings us to our final part, Section 5, the future of therapeutics. Let's just step back for a minute and look at the massive paradigm shift we're witnessing here. Traditionally, if we wanted to harness microbiome biology, we relied on probiotics. That literally means administering live organisms into the human body. And honestly, it's a bit of a chaotic approach with totally unpredictable systemic effects. You just kind of hope the good bacteria do what you want them to do without causing off-target issues. But Biosortia's approach is completely different, and this brilliantly illustrates their concept of pharmacological geofencing. By mining that dark matter and isolating the exact, specific synthetic structures, they achieve precise pharma-grade control. They can design these molecules to only activate locally, say right at the site of a wound, or exclusively within the gastrointestinal tract, which entirely minimizes any systemic exposure. I think it's perfectly summarized by this quote right here. ISMM represents a critical paradigm shift, anchoring artificial intelligence and synthetic biology in finite biological reality to reverse declining discovery productivity. They aren't just using AI to hallucinate drug molecules in a vacuum. No, they're actually grounding that immense computational power into billions of years of real, naturally evolved chemistry to solve a very real pharmaceutical productivity crisis. Which leaves us with this final thought. For decades, we've basically watched our standard antibiotics bounce harmlessly off these biofilm fortresses. But what if the key to defeating humanity's most impenetrable superbugs was already written in the microbial dark matter we've been ignoring this whole time? It just took the right combination of industrial mining, artificial intelligence, and some incredible synthetic chemistry to finally read the code. Thanks so much for joining me on this explainer. Keep questioning what else might be hiding just out of sight.